Picture a thin shell of gas, still glowing thousands of years after a massive star tore itself apart. Deep inside that wreckage, a little over 8,000 light-years from Earth, sits a single point of X-ray light called HESS J1731-347. For decades, astronomers cataloged this object as an ordinary neutron star. When a massive sun dies, its core implodes under its own gravity, crushing protons and electrons together into a single city-sized ball of neutrons, so dense that a sugar cube-sized piece would weigh as much as a mountain. That intense density is the standard fate for a collapsed star. Because this faint point of light lived inside a supernova remnant, researchers assumed it was a standard example of the breed, playing by the rules of known physics. But assuming a distant light is ordinary leaves radical anomalies mislabeled in the archives. It takes a second, closer measurement to reveal that the baseline numbers no longer apply. The turning point came in 2022. A team of researchers used data from the Gaia spacecraft to properly pin down exactly how far away this object actually was. The new measurement showed the star was significantly closer to us than previous estimates had suggested. This diagram illustrates how distance dictates everything we know about a star. If an object is moved closer to us in our calculations, but still looks incredibly faint, its physical geometry shrinks down. It must be a smaller, lighter object. The new math returned numbers that require us to pause. The radius came out to about 10.5 kilometers, and the mass locked in at roughly 77 hundredths of a single sun. That specific weight breaks the physics of stellar collapse. Gravity simply cannot squeeze out a neutron star below an absolute floor of roughly 1.17 solar masses. Below that line, the equations fail. HESS J1731 sits completely underneath the mathematical limit. An object weighing 0.77 solar masses cannot be a neutron star. We are forced to consider that we are looking at an entirely different kind of material. To figure out what could possibly make up a star this light, you have to go past the surface, deep into the impossible pressures of the core, and ask what happens to matter when you keep on squeezing. Under normal conditions, the building blocks of matter are heavily restricted. Every neutron is made of 3 smaller particles, 2 down quarks and 1 up quark, locked tightly together. No experiment has ever pulled a single quark out into the open. This animation shows the theoretical breaking point of that confinement. If you push the density high enough, you dissolve those boundaries. The individual neutrons break down entirely, and the quarks spill out into a shared free-roaming sea. In that high-pressure ocean, a strange transformation occurs. Some of the up and down quarks are forced to spontaneously change into a third, heavier count, the strange quark. You end up with a fluid of roughly equal parts up, down, and strange quarks mingled together. Physicists call this strange quark matter. It represents a state beyond mere density, requiring a total revision of the rules of physics at extreme pressures. A star made entirely of this material would not rely on gravity to hold itself together the way a neutron star does. Instead, it would be self-bound, gripping itself tight through the strong nuclear force alone. Because a strange star is glued together by the strong force, it doesn't need to hoard immense mass to prevent itself from flying apart. That gives it a unique loophole to exist at much lower weights, easily slipping down to 0.77 solar masses. You would know it by its edge. A neutron star gradually fades out into a crust of ordinary atomic nuclei, but a bare strange star ends abruptly. Its density drops to zero like a cliff, leaving a wall of the densest material in the universe pressed right up against the vacuum of space. This 40-year-old theory offers a solution to the modern paradox. A strange star neatly explains the impossible measurements of HESS J1731, giving this impossibly light object a physical way to exist. The hypothesis suggests strange quark matter is the true ground state, the single most stable form of matter in the universe. This diagram shows the consequence of that idea. If strange matter is the ultimate stable state, then a tiny fragment, a strangelet, would act as a seed. Touch it to ordinary matter, and the ordinary matter would find it energetically favorable to convert, falling into that lower, more stable state in a chain reaction. Now, researchers pull on this thread with necessary restraint. Most physicists agree that if strangelets exist, they are incredibly rare, and the conditions to make them stable are difficult to meet. The universe has not converted itself yet. Which brings us back to the faint light in the sky. The identity of HESS J1731 is not settled fact. Right now, there is an active four-way debate among physicists trying to interpret the data. The first explanation is the cleanest. It is a pure strange star, quark matter through and through. The second is more cautious, suggesting it is a hybrid onion star, an ordinary neutron shell wrapped around a core where quarks are just beginning to transition. The third theory rejects the exotic entirely, insisting it is just a normal neutron star, and that our mathematical floor for stellar collapse needs to be lowered. The fourth acts as the wild card. It proposes the object is a standard star laced with invisible dark matter, altering its gravity and mimicking a lighter weight. This balancing scale illustrates why the debate is so hard to resolve. To explain a tiny star, you need a soft equation of state, matter that yields and compresses easily. But we also observe massive two-solar mass pulsars. To hold up that much weight, you need a stiff equation, matter that pushes back hard to avoid collapsing into a black hole. Reconciling those two demands is one of the great open problems in physics. We are left with a single number that doesn't fit the expected model. This anomaly acts as an invitation to rethink, from the ground up, which matter the universe actually prefers.